Yeah, I think in general, I think nuclear has a tendency to be analog as well. So it's kind of a double-edged sword for an engineer coming into nuclear. Nuclear is transitioning already from analog to digital. So there's some challenges moving as we advance the design. One of the things that I think NuScale has done a really good job of in terms of engineering is bring in users and operators very, very early. So we had an opportunity basically to design some of these things. And what's unique about NuScale is I think we did it the right way. The engineering started with the design. So I think you can go and retrofit an analog or a digital control room to an analog system, and it will never be as good as having something built with intentionality from the ground up. So some of the things that are unique to NuScale and SMRs in general are some things like running multiple units from a control room. That's not something you want to retrofit in because you might not get it right. A lot of the engineering that we do and we design for are things that are unique to a multi-module plant. Things like performing the right action on the wrong unit. How do we guide operators to make sure that when they're taking an action on a unit, they're doing it on the right unit? So I think in general, there's a huge level of engineering challenge that comes and creativity as well that gets to come from transitioning nuclear from single unit analog plants to digital multi-unit control rooms. To get to my previous point is there's a lot of things that need to be iterative and designed from the ground up. So one of the things about NuScale specifically is it's an evolution, not a revolution, of the existing stuff, the existing design. So we are a pressurized water reactor. We use the same pressurized water reactors that reactors have used since the 1960s. We use the same fuel. It's one of these things where if you look back at it, you can really, if you've designed it from the ground up and you've got that flexibility, multi-module can be built directly into the system. And from an operations perspective, it has huge advantages over a single unit. So one of the biggest concerns, well, not concerns, one of the biggest problems with existing fleets is refueling. So our nuclear reactor will run for potentially 2 years, and then it needs to come offline. Well, that is a huge power source on the grid that's offline. So at the existing plant, things are worked basically round the clock. They bring in up to 1,000 people. They have to train them, badge them, bring them in, and try and get the unit back online as quickly as possible. For us, refuelings are standard. So with a 12-unit design, you have a refueling every, say, 3 or 4 months, which means you have a dedicated team for that. It also means that when a unit has to come offline for refueling, you've only lost 1/12 of your potential energy. So an 8% loss to the grid instead of a full 100% loss. So in a lot of ways, there's security benefits, there's operational benefits. So not saying that there's pressure in the existing industry to keep a unit online when it's unsafe. It is always shut down. But you make operational decisions about having to lose 100% of your power generation. Whereas for us, 1/12 of our power generation, moving one of those units offline and potentially dealing with it when we have the bandwidth to do so is significantly easier because we're not making a decision that loses a majority of the grid. And I think most operators in the existing industry would recognize that if you could take 8% of your power off the grid in order to buy yourself time to deal with that situation, it provides huge amounts of flexibility. Good question. It's not just our design that's iterated on. It's actually, so like I said before, we're a Gen 3+ reactor, which means that we are all of the stuff that's been from the existing industry. Pressurized water reactors were one of the first reactor designs that was inside of a Navy submarine. So it's not just iteration over our current design, but I'll get to that as well. It's iteration over the design of a pressurized water reactor since the beginning. So that as I said, it's evolutionary, not revolutionary, right? One of the things that we're looking at potentially doing is simplifying systems, and having that be an integral part of the design from an engineering perspective, knowing that you're going to start with a design that's been in operations, tried and true and tested, and you're going to have the operational ability to make it even better is a great advantage. It also means we have all sorts of different advantages for our digital control room, because we can benchmark not just nuclear but existing industries as well. When we were designing our control room, one of the things that we were looking at is, hey, like how do you operate 12 units from a single control room? That's something that hasn't been done in the nuclear industry before. When we looked at the Nuclear Regulatory Commission, they had guidance on how many operators it would take to run these reactors. So they had a table that said, hey, if you run one reactor from a control room or if you run 2 reactors from a control room, but they didn't have anything that said if you run 12 reactors. So when we were looking at potentially how to operate this thing, it was an iterative process. We went and looked at existing industries, so we benchmarked other nuclear reactor facilities that had multiple units on site. That's where we found that one of the key problems that they were running into was right action, wrong unit. So that's fundamentally been built into our engineering process since the beginning. So one of the reactors, we also benchmarked air traffic control. We benchmarked infant ICUs. So different areas in different industries where you basically have to make a decision and things can pile on top of each other. So how do you load follow that across the crew? One of the interesting things about this right action, wrong unit, and its integral part in some of the ways that we've implemented our engineering solutions, is that nuclear reactor that we went to go and benchmark, it had 3 units on site, and it had an elevator. And what happened was, one of the key problems that they had was when an elevator went down, the reactors were basically mirrored. So somebody would go to a different elevator, go up to the same level, turn left and go, and they would be on a different unit. So it was the correct action, but it was performed on the wrong unit. So a lot of our human factors engineering for our simulator itself protects against that. So when we get an alarm, it automatically changes the unit to the appropriate unit on your alarm response. So there's lots built in that you can solve kind of fundamentally when you start at it from the beginning. It's fundamental. Nobody designs a nuclear reactor by themselves, period. There's nobody that knows these disciplines across different areas. I remember I was interviewing a software engineer for our team ages ago, and their response was, well, what I really like to do is take a problem, be left alone, and think about it for a couple months and come up with a solution. And this was one of the things that I pushed back on and said, nobody solves a nuclear reactor problem. Nobody designs a nuclear reactor by themselves. So it's paramount that for our team in specific that we work with all of the disciplines. And my team, as a control room prototype team, it's even more important that I consider what the engineers need and what the operators. Like I said, we're actually on the team of operations. So the other pieces that we have too, kind of as an iterative process through our design, is the longer we've been doing this, the better we get at it. So we have, for our particular software, we go and we pull all the engineering data from different accident analysis, and that gets put onto our servers. So we know what the reactor should do in a loss of coolant accident, how long it should take, what the leak rate is, that type of thing. Well, then we leverage automation, and we leverage good software development principles. So we have an automated test suite that runs nightly and runs a loss of coolant accident and actually compares it to the one that's run by our engineering team. So this is great for a couple of reasons. One, it keeps you kind of like bowling bumpers. It keeps you in the middle of the lane. It lets you know if you've had a problem, so it keeps regression errors at a problem, and it also builds that collaboration. So the engineers can work with us and define kind of the bounding case, and then as we see these different pieces change over time, so For instance, if we put in new automation or controls for a feed water system, the engineers know that basically what we started on was what they approved. And then what we can see is we can actually look and test changes rapidly. So a lot of the engineering stuff can take potentially weeks or months. So one of the key pieces about our simulator is it's an early response tool for engineers to test some operational changes. And that's done by that foundation of having these nightly tests and this collaboration. It's shifted a little bit as I've changed. So one of the things that I found very early on, and as a software engineer, my favorite thing about being a software engineer is my ability to work in different disciplines. So I've worked in defense against bioterrorism, I've worked in government, I've worked in market research, and I've worked in nuclear. So software engineering, I almost think of like a trade, right? You can apply it to other people's industries and learn that industry. So when I started at NuScale, my plan was to help create something awesome, right? To go out and build something that someday I would look to and say, hey, that was my contribution for climate change or that type of thing. And, I started a little over 10 years ago, and now I have a 4-year-old. So to me, it's kind of shifted as well on my perspective of NuScale, because I started thinking, this is like a green energy solution, something I'd be proud to show my friends and family about. And now with a little daughter, I'm thinking to myself, this might make the world a little bit of a better place for her, a little cleaner energy, and how cool would it be to have a fleet of dad helped design these nuclear reactors. So it means the world to me, and I think I'm very proud of having this nuclear renaissance. I think if you ask operators, all of them are green-minded folks. A lot of us believe that stable, clean energy is a solution, especially as we transition electric cars and AI tools. We're adding more and more stuff onto the grid, so having clean energy, to me, I think is paramount. Great question. Now is the time. Now is the time. So we work closely with the Nuclear Regulatory Commission, and one of the things that they're looking at is aging out the existing workforce. So there are grants to try and draw engineers, and not just software engineers, but nuclear engineers and operators and non-licensed operators. Nuclear reactors have been running for close to 60 years, over 60 years. There's a lot of folks on the edge of retirement, and there's a lot of opportunity inside of nuclear. And then as you come in with a fresh perspective, know that it's a great opportunity to make a better world, right? So you have these engineers with talent and creativity that can come in and solve these problems in a slightly different way. And I think the industry needs it now more than ever.